Hello friends, in last lecture we have discussed the examples on error. Now we'll see one example by referring example number 4. So what was the example number 4? That example actually is a voltmeter has the sensitivity of 1 kilo ohm per volt, which is connected across known resistance, and that combination is connected in series with that milliammeter. So we have to take this reference and using that reference, if milliammeter reads 600 milliampere and a voltmeter reads 30 volt on a 150 volt scale, we have to calculate apparent resistance of unknown resistance, then actual resistance of unknown resistance, and find the value of error due to the loading effect of the voltmeter. Also, we have to comment on that loading effect due to the voltmeter for both these examples. So in this case, we are using voltmeter whose sensitivity is 1 kilo ohm per volt. So initially we have to find the total resistance of this circuit. So it is denoted by RT, and RT is voltage divided by current. So voltage reads by the voltmeter is 30 volt, and the current flowing through the milliammeter is 0.6 ampere, that is 600 milliampere. So the ratio becomes 50 ohm. Now the voltmeter resistance is RV is equal to 1 kilo ohm per volt, and whose full scale reading is 150. So the total resistance of that voltmeter is 150 kilo ohm. So the actual value of resistance, which is in parallel with that voltmeter, so that can be calculated. Rx is equal to RT into RV divided by RV minus RT. So RT is 50 ohm, RV is 150 kilo ohm divided by this 150k minus 50. So this product is 7,500 500 kilo ohm, and the difference is 149.95 kilo ohm. So this ratio becomes 50.0167 ohm. Now percentage of error. Percentage of error is the actual value minus apparent value divided by actual value into 100. So actual value is 50.0167. Apparent value is 50. The difference is 0.167 divided by the actual value 58.167. And in terms of percentage, by multiplying the value of 100, we got this value 0.033%. So this is about this example. Now, third type of error is random error. The random error is actually entered after that gross and systematic errors have been substantially reduced or at least accounted for. Means if there is no gross error, and if suppose there is no systematic error, also introduce a new kind of error inside that measurement of the experiment. So that error is the random error. Random errors are generally an accumulation of large number of small effects. So we are not sure about that. This is the particular purpose due to which we are getting the random error. So large number of small effect due to which it accumulates such types of error, and it may be the real concern only in the measurement requiring a high degree of accuracy. So such errors can be analyzed statistically. There are no means we can say that here the errors are due to unknown cause. We are not sure about that cause due to which we are getting such types of errors. So not determinable in the ordinary process by making the measurement. So such errors are normally small, and these errors are follows the laws of probability. So these errors can thus be treated mathematically. For example, for random error, suppose we have one voltmeter, and this voltmeter is used here to monitor the particular voltage after 15 minutes interval. So although suppose we have that instrument, and instrument operate under ideal condition, ideal environment condition means temperature remains same, all the conditions are there actually ideal, and accurately calibrated before that measurement. So all the conditions are good for the measurement of that particular quantity. It still gives a reading that varies slightly over the period of observation. Means we are not getting the same reading after 15 minutes. So their time we are getting the different value. That difference is not too much, but there is a very small variation. So this variation cannot be corrected by any method of calibration or any other method of control. So this error is introduced while all other errors are reduced to near about zero. So means we can say here such types of errors are introduced because of means cause there is no cause due to find that key particular purpose due to which we are getting such types of error. So this is the random error. Now we'll discuss the statistical analysis. Statistical analysis is actually measure is a analysis for measurement of data is important because it allows an analytical determination of a uncertainty of a final test result. Means we have to take number of readings, large number of readings. For making the statistical analysis meaningful, we have to take large number of measurement of usually required. So systematic error should be small as compared to the random error. And because of statistical analysis of data cannot remove a fixed bias contained in all the measurement. See, different analysis are there. The first one is the arithmetic mean. The arithmetic mean means the average value of all the readings. This is the most probable value of measured variable. Is the arithmetic mean of number of readings are taken. The best approximation is possible when large number of readings are of the same quantity is very large. So if there are n number of measurements, then the average value of all the readings x bar is equal to addition of all the readings divided by the total number of readings. So we can write here x1 plus x2 plus x3 up to xn divided by n. So summation of xn divided by n. So arithmetic mean is denoted by x bar, and xn be the n number of readings. Xn is the nth number of reading and n be the total number of readings. Now deviation from the mean. This is the departure of a given reading from the average value. That is the arithmetic mean of a group of readings. So if we want to find the deviation of the particular reading from that mean, so it is denoted by d1. For example, for first reading is suppose x1. Then what is the deviation of a first reading? Deviation of first reading is denoted by d1. That d1 is equal to x1 minus x bar. Similarly, deviation of second reading is denoted by d2, and that d2 is x2 minus x bar. Deviation of last reading, that is dn is xn minus x bar. All the deviation may be positive or negative, but algebraic sum of all the deviation must be equal to 0. So we'll see one example related to these two analysis. For example, here the given data is x1 is 49.7, x2 51.1, x3 be the 50.2, x4 49.6, and x5 49.7. And we have to calculate average mean, deviation of each value, and algebraic sum of the deviations. So here arithmetic mean is x bar is equal to summation of all the values divided by total number of readings. So there are 5 readings. So addition of all the readings divided by the total number of readings are 5. So we are getting the value of 49.86. Then we have to find the deviation of each value from that mean. So d1 is equal to x1 minus x bar. So 49.7 minus 49.86. So it becomes minus 0.16. Similarly, we have to, in this way, we can find the value of d2, d3, d4, d5. So for d5, x5 minus x bar, that is 49.7 minus 49.86. So this value also becomes minus 0.16. This is the third one. See, x3 minus x bar, 50.2 minus 49.86. So this value becomes positive. So algebraic all the sum of deviations. First one is minus 0.16 plus 0.24 and so on. So addition of all these becomes 0. Now average deviation. Average deviation indication of the precision of instrument used in the measurement, and it is defined as the sum of absolute values of deviation divided by the total number of readings. So see, average deviation DAV is equal to mod of D1 plus mod of D2 plus mod of D3 up to mod of Dn divided by the total number of readings n. So summation of all mod of d total dn divided by the total number of readings. So high precise instrument is low average deviation between the readings. See, we have these examples. We have to calculate the average deviation. So average deviation is DAV is equal to D1 plus the mod D1 plus mod D2 plus mod D3 plus up to mod D5 divided by 5. So mod of all the values. So automatically we get the addition of all the values because this is the magnitude. So 1.16 divided by, so it becomes 0.232. This is the average deviation. Now, what about standard deviation? The standard deviation of an infinite number of data is the square root of summation of all the individual deviations squared divided by the total number of readings. Means we have to take the deviation, the square of each deviation and summation of all the square of each deviation divided by the total number of reading. And when we take the square root, we get the value of a standard deviation. Standard deviation is also known as the root mean square deviation. It is the most important factor in the statistical analysis of measurement of data. So reduction in this quantity effectively means improvement in the measurement. So for small readings, means number of readings are less than 30, the denominator is frequently expressed as n minus 1 and obtain a more accurate value for the standard deviation. See, we have an example here. For the given data, we have to calculate standard deviation. So sigma is equal to under root of this value, d1 square plus d2 square plus d3 square up to dn square divided by n minus 1. Why n minus 1 here? Because the quantity number of readings are less than 30. So instead of that n, we have to take here n minus 1. Now substituting all the values, and after that calculation, we got this result. And this result is sigma is equal to under root of all the squares divided by the total number, that is n minus 1, and this addition is 0.292 divided by 4. That ratio becomes 0.073 and square root of this value is 0.27. So this is a standard deviation for the given data. And finally, there is a limiting error. What is that limiting error? Limiting error actually you here used for the manufacturer, for the measuring instrument specify the accuracy within the certain percentage of full scale reading. For example, say manufacturer, when manufacturer manufacture or prepare or made the hold meter, the accuracy of that instrument is a plus minus 2% with that full scale deflection, and that specification is called as the limiting error. So what is the meaning of that plus minus 2% of full scale deflection? So it means that full scale deflection reading is a guaranteed to be within the limit of 2% of a perfectly accurate reading. However, with a reading less than full scale, the limiting error increases. See, we have an example. For example, here 600 voltmeter is specified to be accurate within plus minus 2% at full scale. Now calculate the limiting error when the instrument is used to measure the voltage of 250 volt. Actually, there is a full scale deflection is 600 volt, and whose limiting error is plus minus 2% for that full scale deflection. But when we use the instrument for 250 volt, the limiting error is not same for that value. So how to calculate? The magnitude of limiting error is, so how to calculate the magnitude of limiting error? The limiting error is plus minus 2%, so we have to take 0.02 for the full scale deflection of 600 volt, so it becomes 12 volt. Now limiting error for the same instrument for the voltage of 250 volt, so 12 volt divided by 250 into that 100, so we are getting 4.8%. So 4.8% is the limiting error for the same instrument when we are using for the voltage of 250. Similarly, a 500 milliampere ammeter is specified to be accuracy within plus minus 2%, and we have to calculate limiting error when instrument is used to measure the 300 milliampere. So magnitude of limiting error is 0.02 into 500. milliampere, that is it becomes 10 milliampere. Now limiting error at 300 milliampere is 10 milliampere upon 300 milliampere into 100, so it becomes